So really quick, we're going to describe a short little activity that you can do at your desk today that has to do with conservation of mechanical energy. So you should be getting or have already had passed out this exercise called mechanical energy of a toy car. So basically what happens here is you have this strobe photograph of this ambulance toy car rolling down a hill, and you see how its position changes with time. So each of these pictures have the time interval between each of the pictures is equivalent. So I'm going to quickly take you through how to kind of perform this task here. And most of it is going to be centered around this strobe photograph picture. I know it's kind of pixelated, but this is kind of one of the oldest lessons that I've had from kind of an old textbook. But it does a good job serving its purpose. You can, if you can't follow me here in this video, you can always read the procedure. It basically tells you everything you need to know. But the goal here is, while making measurements from this picture, we're going to fill out this chart. So the first measurement we're going to do is height. So you have to measure from each numbered dot. So notice not every dot is numbered. Measure from the center of each numbered dot down to this 0 line here. So from the center of each numbered dot all the way down to the 0 line in a straight line. So kind of measure that distance for each of those dots. It's hard to kind of control this with the mouse here, but you get the idea. Now you're going to measure those in centimeters, but you will record them using the scale that it says up here, that 1 centimeter on your ruler is equal to 0.1 meters in the photograph. So if you measured something to be, say, 5 centimeters long, it'd be recorded as 0.5 meters because that's the scale of the photograph. The next item on there that you'd want to fill out is the delta D. So that means that's like how they write displacement. So this one can confuse people sometimes. But for that, you're going to measure the distance the car traveled in each of the intervals. Now the numbered dot is in the middle of the interval. So for each delta D, you are going to measure the distance between the two unnumbered dots on either side of the numbered dot. So here's your numbered dot, right here, number 1, and you're going to measure the distance between the middle of the two unnumbered dots. So you're going to measure that distance right there. For dot number 2, you measure this distance, the straight line distance between the unnumbered dot on one side of it and the unnumbered dot on the other side of it. So that straight line distance there. For 3, measure that distance. For 4, again, measuring the distance between the two unnumbered dots on either side of the numbered dot. And that is also to scale. So however many centimeters that is, you're going to convert that to 0.1 meters. So if you got 2 centimeters, it's going to get recorded as 0.2 meters, or say if you got 3.1 centimeters, it will be recorded as 0.31. Okay, so that is how much distance it traveled in each interval. The next column is velocity. So all you're going to do, since the time interval between each dot is the same, you are going to divide the numbers that you have here in your delta D column by the total amount of time that happened between those two dots. Now if you look up here to the instructions, the time interval between each dot is 0.0415 seconds. But we need the time between two dots because that's the distance that we measured. If we're looking at 4 here, we measured the distance between here and here. So the time that you're going to be using is always 0.083 seconds. So you're going to divide the numbers that you have in the distance column by 0.083 seconds. And that should give you an approximation of the velocity of the cart during that time interval. So 0.083 seconds each time. And that's how you get your velocities. Now the end goal here is to calculate the potential energy and kinetic energy of the cart in each position and see how they change. So potential energy is, we should know by now, is equal to mass times gravity times height. That's how you calculate potential energy. Now, the mass of the cart in this is equal to 0.1 kilograms. Gravity, as we know, is always equal to 9.8, and the height is equal to the height that we have here. So that's how you find the potential energy column, is 0.1, that's the mass, times 9.8, that's your G, times the H that we have in the first column. Then the next column is kinetic energy. Okay, kinetic energy, we know, is found by doing this equation, 1/2 mv squared. Okay, so 1/2 times the mass, which is again 0.1 kilograms, times v squared. That's this number that you already calculated. Remember that only the v is getting squared, not the whole thing, okay? Only the v is the thing that gets squared, not the 1/2 mass. So that's how you calculate those kinetic energies. Now, the point of this whole exercise is seeing how mechanical energy changes. We should know that in a perfect world, the total amount of mechanical energy always stays constant. That's what the law of conservation of mechanical energy says, is that the total amount of Ke plus Pe always stays the same in any closed system. Now, in physics, we kind of idealize things to, ignore friction and air resistance. So we first like to think about what it should be in ideal circumstances when there is no friction or air resistance. So remember, these are your initial values, and these are your final values. So Ke plus Pe initial equals Ke plus Pe final. Now, how to find your mechanical energy in this column, it's just the sum of Ke plus Pe, because that's what mechanical energy is. Now, if mechanical energy is being conserved, that means that this number should be staying roughly the same the entire time. Now, remember, this is a real life situation that was plotted in this position, strobe photograph. So we're not, that might not be the case because it is a real world situation, so there is air resistance and friction and things like that. So now we know how to calculate each and every column. Height we measure, delta D we measure, V is calculated, potential energy is mass times gravity times height, kinetic energy is 1/2 mv squared, and mechanical energy is Pe plus Ke. Now it is useful to try and imagine, to double check ourselves, how these values should be changing. As you move down the interval. So if you're looking at the picture here, okay, 1, 2, 3, okay, we should see the height going down. Kind of stays roughly the same here in this middle area, but in general, this number should be getting smaller. Delta D, now that the distance it travels in each interval, in general, the car is speeding up the whole time. Again, kind of staying the same when the track is flat, but in general, we should see these numbers getting higher. The V's, because the delta D's are getting higher, those should also be getting higher. Potential energy relates to height. Height is going down, so that means potential energy should be going down. At no point should it ever be increasing. It might stay kind of the same in the middle, but it should always in general be going down. Similarly, kinetic energy, because it relates to velocity, and we're speeding up as we go down the track, kinetic energy is increasing, and so that number should be getting higher. Now, in idealized circumstances, this column, every number in here should be the same, because what we're losing in Pe is equal to what we're gaining in Ke. Okay, or so says the law of conservation of mechanical energy. But again, that may not necessarily be the case. You may see that this total amount of energy has reduced as it goes from the first interval to the last interval, meaning that it lost some energy somewhere. Energy, of course, is not always lost per se. It just goes into forms that we maybe don't want it to. And that's what you kind of look at when you look at these few simple questions down here. So it's talking about what other types of energy are going in there. Remember, friction can do work on objects. Here, when it says what percentage of the original mechanical energy was left at the end of the trip, that means you're going to take a comparison of your first and last value down here to find what percentage was left at the end. You'd take the last number, divide it by the first number, and multiply it by 100, and that would give you that percentage. This number should definitely either be the same or less than this number. Sometimes people measure a little weird, and that's not always the case, but this value should definitely not be going up at any point. Also, it refers to a graph that you're supposed to make. It's just saying that if you don't necessarily need to make that graph, but this one just asks, if total mechanical energy did remain constant and we plot it on a graph of energy, what would the graph look like? So that just means that if you have a simple graph of energy versus time, what would that graph look like? Would it be going up? Would it kind of look like the track does, like kind of swervy, go flat across? What would it look like? It does mention on the front that it wants you to make a graph under instruction number 7 here. On a single set of axes, draw a graph of energy versus time. Plot a curve representing potential energy, another curve representing kinetic energy. So you don't necessarily need to do that, but it's worthwhile understanding what that graph would look like. Again, just a simple, XY graph where you have one line for the one type of energy. That's, of course, not what it looks like. Another line for the other type of energy. So you can do that if you want to help you answer the questions, but not required for what I need out of this. But again, it might be worthwhile to understand what it may look like. If there are any questions, please let your teacher know. I'm sure they will be able to figure that out. But should be pretty straightforward. All the instructions are there, so if you're not sure, if you couldn't follow me as I described it, just read through the procedure and follow along. Like I said, always double check yourself by looking at your chart. These values should be decreasing. These should be increasing. These should be increasing going down. These should be decreasing going down. These should be increasing going down. And these should either be staying the same or in general going down. Good luck. Should be able to hopefully finish by the end of class. Thanks.